Okay, in digital design, we can simple the behavior of NMOS and PMOS transistor to switch level model. So for NMOS, we can say that when the get point is high, the switch is turned on. When the get point is low, the switch is turned off. For PMOS, when the get is low, the switch is turned on, and when get is high, the switch is turned off. We can just simple the behavior of the MOS gate to a switch level model. And we can draw a symbol of NMOS. You can just write a symbol like that. For PMOS, you can write a symbol like that. The difference is only here. If this transistor is low enabled, you can say low voltage turned on. So we can draw a small circle at this point. If it is high voltage turned on, there is no small circle. So as you can see, in digital circuit design, a small circle always, most of the time, a small circle denotes low active. Okay, you have to remember the switch model of the MOS gate and the symbol of NMOS and the symbol of PMOS. This is just simplified for digital IC design. If you are doing analog circuit design, you can't treat them as simple as that. The analysis of PMOS and NMOS will be much more complicated. You have to refer to the analog circuit design book to study. Using PMOS and NMOS, we will try to build an inverter. That is, it can do a function like that. The output is not A, not the input. So let's see how it works. This is the PMOS, yes. This is NMOS. So let's see how it works. If we give a high voltage such as VDD, which transistor will turn on? This one will turn on, yes. So this one is turned on. The output will be collected to GND. So the output will be collected to GND. GND is 0. So the output is 0. Okay. How about when we give a 0 in the input? This is low voltage. For this time, the PMOS is turned on, and the output will be collected to VDD. This will give the output a high value, high voltage. So as you can see in this truth table, the function of the output is just the invert of input. A equal to not no, Y equal to not A. We have used the MOS transistor to build an inverter gate, inverter logic gate. This is a symbol of inverter logic gate. Okay, let's reverse back. You need to try to think about it. Why most transistors can form an inverter? can we use diode? Can we use diode to build an inverter? Can we use diode to build an inverter? It seems impossible. It seems impossible. For the MOSFET, you have 3 pins. This is the control pin. You can say this is the control pin, and this is the signal pin. This is the signal input to the signal output. You have the control pin to control whether the signal can go through this cell, can go through this device or not. Yes, you have the controllability to control whether a signal can go through from source to drain. But for diode, you didn't have the control point. There is no control point. The signal can just go through or not go through. So this may seem why we can't use diode to build an inverter. Okay. So in this page, you have to know the function of an inverter and the symbol and how it's built up using NMOS and PMOS. Okay, let's say the inverter output responds to its input. This is the inverter, this is the PMOS, this is the NMOS. If we give a voltage on this point, if we give a voltage, the waveform is something like that. What's the output? What's the waveform on the output? The output is something like the figure shows. The output curve is something like that. From this figure, you can see when the input changes from from low voltage to high voltage, this transistor will turn on. Let's explain this part. To low voltage, and this point. At this point, this transistor will turn on. To low voltage, this transistor will turn on, and we will charge this capacitor. That is, there is current flow to this point, and charge this capacitor, and the voltage of the capacitor will go up. Okay, let's explain this part. And we assume there is already high voltage. There is already high voltage at this point. High voltage. The begin point is high voltage at this point. When the input voltage change from low to high at this point, this transistor will turn on, and this will turn off. So the electric stored in the capacitor will discharged through this path. This is to GND. It will discharged. So the voltage on this point will change from high to low. Okay, this is the behavior. And there is still something interesting we need to explain here. First, can the output be changed in this form? That is, it's a right angle. The form is a right angle, 90 degree angle. Can the output be changed in this curve? The answer is no. The answer is no. This is because even if the transistor is turned on, it has resistance. You can treat it as a resistor. So let's assume this is VDD, and this is turned on, this is cut off, and we can simplify it as a resistor. So we can simplify the charging process as a RC circuit. RC circuit. The charging of an RC circuit. If you have basic circuit analysis knowledge, you will know at this point it can't go straight up. The waveform is something like that. Go up, there is a slope. And this is the same for the discharge. Okay, this is the first thing. The signal, the real signal in the digital circuit can't go straight up or straight down. The change from low to high and from high to low, low to high, there is always a slope. This is a slope curve. This is the first thing. The second thing, you need to note from this figure is, it seems that the time for the signal to change from high to low and the time for the signal to change from low to high is different. Yes. Or we can say for most of the time they are different. Why the time are different? This because they go different paths. For charge, they go this path. Yes. And for discharge, they go this path. And the resistor for this path and for the PMOS transistor and for the NMOS transistor is different. The resistor is different. So the curve is different. This makes the time different. This makes the charging and discharging time different. Okay. So you can say the charge. The second thing is the charge and the discharge time is different for the same cell. Okay, in digital design, we treat the value of signal as 0 or 1. 0 or 1. There is no value between. So we can change the waveform of the input and output to this form. Okay, sorry, they are not matched. Okay, they are not matched. This is a high value, but the beginning is a low value. Okay, you can say, you can treat this that this is the 0.1. Okay, this is 0.1. This is 0.2. Time 2. This is time 2. Okay. So we can denote the signal. If you draw a picture, you can just draw signal like that. A line, a line, a line. You don't need to draw it like that. This is the input of the inverter, and this is the output. And this slope denotes the time of this period. This is not right. This. Okay. And this time denotes the time of this period. Furthermore, you can even sample the digital form as this figure. You can omit this part, just draw it as a right angle. Both are acceptable in digital circuit design. Oh, sorry. Okay. The most important part of this page isn't how to draw the signal form in digital circuit design. It's the defining of 0 and 1. Okay, it's the defining of 0 and 1. Let's come to this. In digital circuit design, we have the value of 0 and 1. So the defining of 1 is usually 80% of the VDD. If you have a voltage above 80% of VDD, we call this is 0. This period is 0. No, this period is 1. If you have a voltage of below 20% of VDD, we call it 0. So this part is 0. Okay. And for the voltage between them, we just call it the unknown region. They are not either 1 or either 0. This is unknown region or unknown value. So in digital design, we use X to denote unknown value. So you can say this part is X. For this period, the value of the signal is X. For this period, the value of the signal is 1, 0. For this period of time. And please note that the defining 80-20% may change from process load or cell library. For advanced load, such as 19 nanometer and below, this may be 70% and 30%. You can find this number in the cell library. Okay. So in this page, you need to understand the defining of 0 and 1 in digital circuit and the value of X. What's the value of X in digital circuit? And how to draw waveform in the digital format. Okay, so for digital and analog circuit, this is an example of difference. Digital, we just have 0 and 1. For analog, you have the continuous value. Okay, from the VDD to GND, you have a continuous value. Let's go on with two important defining of transition and delay in digital circuit design. Transition. The defining of transition is the time used for a signal of a same load, for example this load, to change from 0 to 1, or change from 1 to 0. This is a rising transition, and this is the falling transition. For example, this time is falling transition for this point, for the y point, and this time is the rising transition for the y point. This is transition. The key point here is transition is defined on this same load. On this same load. It defines how fast the signal can transition from 1 to 0 or 0 to 1. Now, let's go on with the delay of a cell. The define is, for a same cell, the time between the input cross 50% of VDD to the output cross 50% VDD. So it's related to 2 points of a circuit, such as for the example of an inverter, it's related to A point or A load and Y load of a circuit. A and Y are not the same point. They are different points. So this is the delay from the input cross 50% to the output cross 50%. This is the delay. And this is also a delay time. 50% to 50%. As with transition, we also have falling delay and rising delay. This is related to the output. If the output is rising, we call this delay a rising delay. If the output is falling, we call this is a falling delay. As we have explained here, the output falling transition and the rising transition is usually different for the same cell, as they go through different paths. Based on this, can you find out the delay, the rising delay and the falling delay for the same cell is equal or different? The delay is different or equal for the same cell. Please have a think. Okay, let me explain it in a simple figure. Please see this figure. Let us assume the input signal is a right angle, and you can ignore this part. Ignore this part. Okay, ignore this part. We just focus on this part. This is the output with small transition time. At this case, the delay is from input 50% to output 50%. This is about this long. Okay, this is the delay. If we increase the transition time, you can see what will happen. If we increase, okay, so the delay will be this. Yes. So as you can see, because the output transition is different, so the delay of a cell usually different for rising delay and falling delay. Okay. And this page you have to understand the define of transition and delay, and usually for the same cell the output transition of rising transition and falling transition are different, and the rising delay and the falling delay are usually different for the same cell. Okay, let's go on. If we have designed a cell, we have drawn a cell, or let's say we have manufactured this cell in the real silicon. We have manufactured it. Is the delay of the cell is fixed? We have manufactured it in the real silicon, in a real chip. Is the delay of this cell is fixed or not? The answer is low. There is some factors will affect the delay of the cell, such as the process. Okay, let's ignore this first. Let's explain this one. Voltage. The supply of the voltage may change from case to case. If you give the higher voltage on the VDD, the delay will be small. If you give slow voltage, a smaller voltage, the delay will increase. And for a real device, we usually require that the variation of the supply voltage can change within the range of 10%. For example, if you say you wanted the circuit is working at 1.1 watt. So in the real application, it should working. If we give it a voltage of and this gives 0.99. This is about 0.21. So if we give voltage in this range, the circuit need to work. You can imagine if you design a PCB board, how can you make sure the voltage is exactly 1.1 watt? This is impossible in real application. Okay, so when we design the chip, we usually give a range. In this range, we will make sure the IC still works. This is one variation. The second variation is temperature. This is the temperature of the diode, such as the diode is this point, is the temperature here and here. Okay. Another variation, such as the temperature in the morning and in the afternoon is different. The temperature when the IC is just begin up, is just powered up, and when it has been worked for an hour, is different. So we usually give a range. In this range, the circuit must work correctly. For consumer usage, we usually guarantee this range. For industrial usage, the range is expanded to such. And for automotive, it's further expanded to this. We have explained two variations that will change the delay of a circuit. And for temperature, it's usually the temperature is higher and the delay is bigger. And if the temperature is lower, the delay of the cell is small. So you can say even if the cell has been manufactured, the delay can change. Okay, and the third variation is process. That is the process when the cell was manufactured. there is some variations in process, such as when doping, okay, for this page, if I have designed two cell with the same size and the same type, that is, they are the same cell in the cell library. They are in the same cell in the library, but they are at different location of the die, such as this cell 1. They are the same. They are the same cell. They are the same in water, but they are in the different place of the die, where the delay of the two cells are the same. Let's assume the voltage supply and the temperature of the two cells are the same, where the delay of the two cells is the same after manufacture. The answer is no. This is because when manufactured, there is some variation. For example, the doping. We can't make sure the doping of this area and this area. So if you say in a die, the doping of this area and this area is exactly the same, we can't make sure. And we can't make sure the length, the channel, we call this a channel, the channel length, the channel length of this cell and the channel length of this cell is the same. And also we can't make sure the capacitance we build here for this cell and the capacitance we build here for this cell is the same. So these factors will affect the delay of the two cells, even if the two cells are the same cell in the library. Okay, this is may confuse, but you can say that, can you find two cars with the same weight and the same size, even if they are a car of the same type, such as BMW, dash. Okay, even if the two car is the same type, can you find two cars with exactly the same weight, the same color, the same consume of oil? Let's give a simple example. Can you draw two wires of exactly the same length? Can you draw two lines of exactly the same length? This is impossible. Okay, so this is the same for the transistor manufacturer or IC manufacturer. The foundry can't make sure the two cells of the same type be manufactured exactly the same. So there is some variation at the manufacture process. Okay, for the three variations, we denote them as P, V, T. We call them PVT variation. So through the explain, you can understand the PVT variation is some variation the designer can't control. You can't control. Yes, there are variations in the real application environment. And in later section, we will explain some other factors will affect the cell delay. But these factors are intention factors. We are designed to make the delay of the cell big or small. This is intention factor. And these factors are controlled by the designer. Now we will explain these factors in later section.